The title of my talk today is Artificial Intelligence and Next Generation Networks. I had a bit of difficulty to actually figure out what the title of my talk should be today, because I am a communication network person, basically. Okay? Communication networks is my background, and then gradually I started working on cyber-physical systems as well, also called Internet of Things. But as you guys may already have known, at least almost by the end of this winter school, that artificial intelligence or machine learning, or more recently deep learning, people are trying to use it in different fields, also made possible with the recent breakthroughs, recent developments. And we are not any exception. So we also try to use the algorithms, the techniques from machine learning, deep learning, AI in our field, in communication networks, in cyber-physical systems. So first, I thought of keeping the title as Artificial Intelligence for Next Generation Networks. And then I thought it's not just for next generation networks. There's a lot that the next generation networks entail to AI as well. It's both ways. And I'll explain more about that in my slides. So then, as common and as odd it may sound, I finally ended up with this title for my talk. That was a bit of a background behind the title. But before proceeding with my slides, I would like to know, how many of you are from a computer science background? Or communication, engineering? Many? Okay. Others? Physics? Chemistry? Okay. Okay, not bad. Yes? Biology. Okay, but in biology also there are many applications of AI, of course. Okay. I'm aware that there is quite a bit of diversity in the background of all of you. I'll try to keep things a bit simple. At least the communication network part, for those of you who are not exactly from the background. But if things get too blur, then you can ask me. Stop me anytime and ask me, okay? And usually what I tend to do is, I tend to speak very fast as I go, and being aware of that, I consciously try to slow myself down, and I'll do the same today. But by any chance, just if I happen to be fast again, then you can just say stop. All right? Slow down. Okay. So after the title itself, I also had to think a bit about the agenda, the outline of my talk, and I divided it into 3 sections. The first one is an overview on next generation networks. What are next generation networks, and why is it important in the context of AI? Or why AI is important in the context of next generation networks? It's both ways. And why it's next generation networks and not current generation networks. The second one is next generation networks for emerging AI applications. So the first one and the second one, they are quite closely connected. So you will see as I present that there is a bit of the margin between the two is also a bit blur, but I'll try my best to keep them in the 2 sections. And the third one, AI for next generation networks. So what can AI do, or what kind of problems will AI solve in next generation networks? And again, as I also mentioned before, communication networks are a very big area in itself. AI is, again, a very big area. And here we are talking about both. So it's not possible to cover everything about AI and everything about next generation networks. Not even many of them, but I will just take this example, learn by example approach. So I'll cover some of the topics, may not be able to cover many, but some of the topics, and I'll give examples of some of the research topics in the area. And I'm sure that you have learned a lot about AI. Many of you probably knew about it, had knowledge about it from even before. But in the last week, maybe in the last 8 days, you've learned much more about the algorithms, about the techniques, about the mathematics. So I'll not be focusing on the algorithms or the techniques themselves, but I'll be focusing more on state of the art, the research challenges in different areas. Communication networks, next generation networks, and also in AI, and the synergy, of course. Okay? So, an overview of next-generation networks. So, recent breakthroughs in AI, especially in deep learning, they have enabled computation of tasks that once seemed impossible, and consequently have also revolutionized multiple fields. There are many of them. I've just included some of them as the examples. Industrial robotics, healthcare, autonomous driving, smart grid, electric vehicles, agriculture, and many more. All of these fields, or many of these fields, actually more than these, can get benefits, can take benefits from the breakthroughs, the advancements in AI. What are the key components of those breakthroughs, or what are the components that play crucial roles in the recent advancements? Computation power, yes. Data source, data generation, and data availability, all of them. Now we have more data generated than ever, more data publicly available than ever, yes. And of course, also the algorithms. Although the first two parts, computation power and data, has seen a lot of work recently, relatively less in algorithms, I would say. But parallel developments in communication networks, or actually next-generation networks, are also crucial to fully embrace the revolution that AI is about to bring, or that we would like to hope that AI is about to bring. Okay? Why? You see, these applications or use cases, autonomous driving, that will be generating about 1 gigabit of data. If a car has to drive itself, it'll generate 1 gigabyte of data every single second. And how much is 1 gigabyte of data? Smart hospitals, they can generate up to 4,000 gigabytes per day. And connected factory, automation industry, about 1 million gigabytes per day. That's a huge amount of data. And these are in seconds and days, in one day, not in months and not in a year. Okay? So when the data is generated, of course, you can make the use of that data. The learning techniques and the data analytics, they go hand in hand. Okay? But then the data is generated. You do not analyze the data or consume the data locally. You generate the data, maybe some of it also for your own self, but then most of it, almost 100% of it, you have to transmit it somewhere else, to a remote server, to the cloud, somewhere else, to the control center. You have to transmit the data. And how do you transmit the data? I saw many hands when I said who is from computer science and engineering, communication engineering background. Come on, guys and girls. Yes? Louder? Over the internet? You said FTP, okay. Wireless networks, okay, very good. Yes, it's all of them, right? A part of the network will be through the internet, the core network, but FTP also. But you also have a part of the network which is actually wireless. It's called the radio access network. When we make a call or when we browse over our phone, it is not transferred through the wired network directly. Before reaching there, it has to go through a base station, right? That's wireless. This part is wireless, called radio access network. And if you have to transmit 1 gigabyte per second of data through every vehicle, and there are so many vehicles on the road, and if you have to do that wirelessly, how crowded the spectrum will be, and how efficient or how good this whole thing is going to look like. You can imagine, okay? So, communication networks, parallel developments in communication networks are equally important. Now, we take a step back and remember the history of mobile networks, mobile communication networks, very briefly. 1980s, it was the first generation of mobile networks called 1G, but people take 2G to be the official standard of mobile networks. But anyway, 1980, it was in 79 actually. That was mainly the analog switching technology, and it was only voice. And then in second generation, a digital technology called GSM, Global System for Mobile Communications, I think, came, and then SMS and limited email services became possible. With 3G, video calling became possible with higher data rates, and also the use of smartphones began in 2000s. And then with 4G, even higher data rates became possible, so we could browse, we could download stream videos, and we could watch movies on our phones, and that's from 2010, and the speed is getting better. The data rates are getting better. 2020, now we are in 2018, but 5G is expected to go on the floor commercially from sometime this year. Now it's almost the end of the year, but 2018-19. There has been many prototypes, many experiments all over the world, but the 5G deployments are commercially about to start. I also read somewhere that Korea was planning to start the official deployment, commercial deployment of 5G some 2, 3, 4 weeks before. I'm not sure, I haven't followed up on that, but yeah. So this is also starting, and with 5G it'll be extremely high data rates, and it'll be new technologies, millimeter waves, and many new, novel, and innovative applications. Well, that was a bit of a history on the mobile network side. So what is happening with the users then? With users, here, if you look at 1970s and then 2000s, here we are somewhere over here, I think. The explosion of connected things, connected device, has really shown an exponential growth here, here, and here. And then it is predicted that by 2025, there will be 50 billion things connected in the world. Things. So things are basically everything. Okay? Devices, equipment, machines, big machines, small machines, even people. These days, people can have chips in them, within them. So everything, basically, and that will amount to some 50 billion. That's what is the prediction by 2025. Okay. Internet of Things. Have you heard about this? This term? Yes? Just some of you? Just some of you have heard about it? Yes. Okay. What is Internet of Things then? Would someone like to speak a bit louder? Yes? Thank you.
Internet of Things is like in devices and like electronics connected and sharing information autonomously and interacting with each other.
Yes, yes, very good. Well, I have the definition right here, so probably was not a good idea to ask. But I trust that you said you give me the definition without looking at my slide. Okay? Yes. Basically, Internet of Things. Internet is the connection between two entities or multiple entities, right? So Internet of Things it's the connection between things that are connected, and things that are connected anytime, anywhere that can collect and exchange data. That's Internet of Things. All right. Why is this Internet of Things concept so important? Why is it important? And it hasn't been many years that the concept came. I mean, well, it has been some years, but now it's getting more and more important. Why do you think it's so much more important now? Makes life easier?
Yeah.
Okay, very good answer.
When we say all of our devices connected to the internet, so everything will be possible for us to, well, share information. At the same time, we can aggregate data. Mm-hmm. Similarly, if you aggregate data, it can form insights about people. So you can now, if you're a business, you can target people based on their based on personalization of the things that each person needs, wants, mm-hmm. and at the same time, it can also be used for population-based, population-based dimensions, wherein communities can be now targeted based on basic services.
Okay. Very good. Thank you. Well, you went a little bit too far, I think. What I asked, but that's correct. What you said is right. But what I asked was, why is it so important? Why is it more important than before? The reason is the behavior of the behavior of people. The people who used to be data consumers before is now changing. Before, they used to be just data consumers when 3G began and when 4G began. It was from somewhere between 3G and 4G. Some people call it 3.5G and 3.75G, actually. But then they were mainly data consumers. Okay? There would be services, there would be data centers, and then people would browse, people would download videos, and other files, multimedia. But then they were mainly consumers. But now people are becoming also the producers of data. Okay? So the end users are now becoming prosumers. They are no longer consumers. That's one of the main observations and also one of the main motivations. For example, YouTube users, they upload about 100 hours of video every single minute from all over the world. And Instagram users, they post about 2.43 million pictures every single minute also. And these numbers, they are probably from last year or maybe the year before, so they are not the recent, the most updated values, but I'm sure that they shouldn't have gone down. They should only have increased. Okay? So it's safe to put those numbers here. So that's one of the main motivations. And then this is verified by Cisco, verified and also a bit projected. And Cisco anticipates that there will be about 49 exabytes of data per month, data generated per month by 2021. Exabytes of data. How much is 1 exabyte? It's gigabytes, then terabytes, then petabytes, and then exabytes, and then zettabytes, right? So it's 10 power 9. 1 exabyte is basically 10 power 9 gigabytes, right? So that's a lot of data, actually. Now, so we know that there is a lot of data coming in. Okay? A lot of data coming in, and people's behavior is changing. We have some communication networks. Some communication networks are to be deployed by 2020. So what happens is, in this case, there's data coming from the producers, and those may just go to the cloud or to the servers or the control center, or they may also be consumed by other data producers, which are consumers of that data, but they may as well generate data at other times and other places. But in that case, the whole thing is okay, but you know, this part, where it is wireless, that can be the bottleneck. If you're really asking for too much data to download, or even if you want to upload too much data. Not just you, but in total. Okay? And how much is too much data? So IoT devices produced, the data produced by IoT devices, it's a little bit. Okay, the data produced by IoT devices recently reached about 500 zettabytes. So it was exabytes before, now it's zettabytes, but this is in total. And about 5 gigabytes per second data is generated by a Boeing 787. So why these numbers are important is just to give you a feeling of, you know, how much resources do we have for transmission. I'm just trying to relate everything to communication networks, and then the resources we have for storage and computation, because these are really important. Okay, that's a lot of data basically. All right. Now, then the emerging applications, in addition to generating a lot of data, many of them, not all of them, many of them need intensive computations. Therefore, intensive computation resources, and also in some cases ultra-reliable communication, the transmission, and in some other cases ultra-reliable and low-latency communication, or ultra-low latency communication, critical applications, okay? Now, in this case, we take the example of autonomous driving, a self-driving car that generates about 1 gigabytes per second of data, and then all the data that it sends to the control center or to the cloud, that has to be processed almost in real time, within a few milliseconds, and it really depends on how many milliseconds, 2 milliseconds or 15 milliseconds or 100 milliseconds, but within milliseconds, okay? Now here, what we try to do is, these are some data from the self-driving car. So you see some hands here, but yes, these are from self-driving car, and they go to the cloud here, and the data can be processed, and the computations can be performed by the cloud, because clouds have a lot of resources, good enough resources, we believe. But then the problem here can be that because the data has to travel too far, even though the network is actually wired, but a part of it is wireless, so then the wireless network, and then the wired network, and then the computations happen there, and then the result comes back. So that is going to take a lot of time. And you may ask, how much is a lot of time? Is it 10 seconds? Is it 10 minutes? It's not 10 seconds, it's not 10 minutes, maybe it's milliseconds, but still, it can be a lot of time. Imagine a car is driving itself at 100 kilometers per hour in a bend, and there is another car coming at the same speed. And then you are sending your data to the control center, and you're waiting for, it has been 35 milliseconds, the data comes in 40, you get the data in 45 milliseconds, but you have to actuate your actions Hello? Is it better now? Somebody told me that there was a lot of disturbance. Sorry for that, but this is better, I hope. Okay, good. So just some more examples. If we talk about factory automation, then we need latencies in the order of 0.25 milliseconds to 10 milliseconds. 10 milliseconds is still okay, but 0.25 milliseconds, think about it. Intelligent transportation systems. I'll talk about a concept, a paradigm called Internet of Vehicles after a few slides. But for that, we need, depending on the particular application, from 10 to 100 milliseconds. Smart grid. Have you heard about smart grid? Yes? No? Okay. Well, we are not. We will. I don't have others. We will not be talking about smart grid today. But smart grid is. We know conventional power grid, right? Smart grid is the power grid that integrates ICT into it for improving the efficiency and reliability of the power grid. Okay? A bit simplified definition, but for now I think that should be fine. And the PLRs here, you see. Packet loss rate, yes. I heard that. Packet loss rate for factory automation, it's 10 to the power minus 9. What does that mean? You can afford to lose one packet out of 10 to the power 9 packets. Otherwise, you cannot meet the performance requirement. Okay? And when do you lose the packets? When you transmit them. In the case of intelligent transportation system, ITS, 10 power minus 3 to 10 power minus 5. So it's not as bad as in the case as compared to factory automation, but still, 1 out of 1,000 packets, 1 out of 100,000 packets you can afford to lose. When it comes to smart grid, then 3 to 20 milliseconds, and packet loss ratio of 10 power minus 6. In fact, in smart grid, there are many applications, many different components. I've been working on smart grid also from quite some time. So the latency requirements vary from about 2 milliseconds to also 5 minutes, because the applications are really diverse. Okay, but I think 3 to 20 milliseconds, this is considering the critical applications within the smart grid domain. Now, we talked a lot about what are the requirements, how should things be, what can we afford to lose, what can we not afford to lose, but then what do we have currently? Well, what the communication networks that we currently have, what is the communication network that we currently have? Is it 3G, 4G, 5G? Yeah, 3G and 4G, I would say, at least in Nepal, right? There has been many measurements, many experiments all over the world. We also had, in Norway also, we had, not me, but some colleagues of mine. There's a group, we have this measurement test bed all over Norway, throughout Norway, and we did measure the reliability performance of LTE 4G, and that complies very well with the measurements conducted by Ericsson in 2016, which says the achievable end-to-end latency is about 21 to 43 milliseconds in the best case. So that's about 32, 33 milliseconds in the best case. This is end-to-end from the user, one user equipment here, and then the access network, the core network, and then another user equipment there. Median is about 33 to 75, that's 55 milliseconds, and then in the worst 10% case, this will be more, almost 200 milliseconds. Okay, this is what we have. Do you see the gap? So we want end-to-end latencies to be 1 millisecond, 0.25 milliseconds, 2 milliseconds, 5 milliseconds. This is the performance that we can achieve with the 4G networks, with LTE networks that we have today. And these are also two plots from the measurements that Simulamet, now Simulamet, but it was similar before, conducted back in 2013, 14, 15, I think, where we show the reliability performance, fraction of connections here, experiencing the RTT, round trip time of such and such milliseconds, okay? For two different operators in Norway. And here you see that this one is the purple one, that's for Telia in Norway, and the green one is for Telenor, Norway. That's the biggest telco in Norway. And the red one is Red one corresponds to the case when we combine both the networks. It's called multi-connectivity, which means you have a node and you can access both the base stations. Okay? So you can transmit your signal using Telia base station, or you can transmit your signal using Telenor base station. And it's, of course, in terms of resource optimization, it can be a bit of its redundancy, redundant paths. Yes? You understand that, right? So it's a bit of redundancy, but then you will see here that when the required level of reliability is not as high, 99.99, we call it 4 nines, and here it's 5 nines, then the multi-connectivity, it's actually dual association or dual connectivity, that does not necessarily perform better. Here, you see, these two curves, they have a higher performance. But then, as you need very high reliability, above 5 nines, then more fraction of nodes, more fraction of connections, they experience better reliability. Okay? So the reason why I showed these two curves is multi-connectivity is another very hot topic, or at least it is expected that it will be one of the hot topics in 5G in future, one of the hot research topics as well. Again, a little bit more about multi-connectivity, path redundancy, and overall reliability. Just to give you an idea about what is the reliability performance required of single paths and how will that be in multiple paths or multiple connectivity when you need an overall reliability of very high overall reliability. Okay? So you see, if your single path, one path has a reliability of 90%. Reliability is 1 minus packet outage rate, right? So reliability of 90%, and then you actually need a reliability of 99.49, so total 6 nines. Then you need 6 different paths to actually get from 90% to 99.6 nines, basically. And if each of your path has 99% reliability, see, 9% up from here, in that case, you may just have 3 different paths, 3 redundant paths, to get 6 nines. And if you have 99.9, then 2 paths would do. If you have 99.99, then even with 2 paths, you can get some 8 nines. And with 5 nines here, you will get, well, it's never 100%, but very, very close to 100%. And why is it so important to talk about from 4 nines to 5 nines? Why does somebody bother about 99.99999? And you see, why is that important? You might be wondering, right? Maybe some of you are not wondering, but many of you are, I'm sure. So the reason it is important is, see, it's not as difficult to improve your reliability from 80% to 95%. Okay? But then to go from 95% or to 90%, and then from 90% to 98% is more difficult. From 98% to 99 is even more difficult, and then from 99 to 99.9 or from 99.9 to 99.99 is very difficult. But it is so difficult, and it sounds or it looks so useless, but still it's important, because if you go back to some of the slides, some of the numbers in the slides where we talked about the reliability, remember there were packet loss rates required of 10 to the power minus 9, 10 to the power minus 6. So what is 10 to the power minus 6? 99.5 or 6 nines, is it? 5 nines? So that is what we need, maybe 5 nines. And 10 power minus 9, which means 99.5 nines is not sufficient. So that means it's basically this one, right? Okay, so you can have 2 paths, multiple, 2 redundant paths, but then each of them should have 99.999% reliability, which is usually very difficult, so you need to have more paths. That's what it basically means. Okay? Any questions so far? Questions? No questions? So it was everything that you knew already? Nothing interesting? No. Okay. Oh. All right. So now the second part, where next generation networks for emerging AI applications. As I also mentioned at the very beginning, this is kind of closely related to the first bullet over there, the first section. They go hand in hand. but then I'll try to talk about some key areas, hot topics in this area, in this field. Okay, again, this is a very strange kind of a figure that I made, but I'll try to explain what I mean by this. So next generation communication networks should be capable of accommodating the communication needs of other next generation networks. So what does that mean? Is next generation networks are basically networks or systems, cyber-physical systems or cyber-physical networks. That can be a communication network, that can be some other kinds of networks or some other kinds of systems. For example, communication network is a next generation communication network is a next generation network. It's a special case, right? And next generation vehicular networks are also vehicular networks or Internet of Vehicles are also next generation networks. Smart grid, cyber physical system, and there will be this underlying communication network and smart grid as well. That is also a next generation network. Sorry. So basically, communication networks are a part of the next generation networks. And then how do we see artificial intelligence, or how do we put artificial intelligence? Where do we put it here? It's connected to both of them. Well, I mean, okay, if it's connected to this one, then of course it's also connected to communication networks. But the relationship is slightly different here, because communication networks, they can enable or facilitate at least all different networks or systems that are now being revolutionized by artificial intelligence. Okay? Does that make sense? No? It doesn't make sense. Okay. So what I'm saying is, next generation networks or next generation systems that need ICT or communication networks because they need to transmit data. And they need AI and data analytics to make use of the data that they are generating. Yes? Is that true? That makes sense? Okay. So basically, communication network is an enabler for many other next generation networks, and AI is also an enabler for those networks. Yes? Okay. And communication network is also a part of this general umbrella of next generation networks. Okay? Yes? All right. That is what I wanted to say, basically. All right. Then what is the next generation communication network? Then we come to 5G. Now, people are already working on 5G beyond or 6G, but we'll stick to 5G for today. And in 5G, there are a number of underlying paradigms and technologies that will make it possible, the requirements, the goals that come with 5G. And we will not be talking about all of them, of course, but probably some of them, one or two of them. Network slicing, that's a very important concept in 5G. Do you know what is network slicing? Someone? Okay. So network slicing, what you do is you have the same physical infrastructure, but you divide it into different slices, okay? Because you have a number of different applications to meet the performance requirements of. So even with the same physical infrastructure, you divide them into a number of layers, and then one particular layer to meet the communication performance requirements of this particular application, or another layer to meet the performance requirements of this particular application, and so forth. That's a network slicing. Massive MIMO, multiple input, multiple output, massive antennas. Device-to-device cell-free device-to-device communication. Cloud RAN, radio access network, cloud architecture, ultra-dense small cell networks. Network densification, anybody? No? So network densification is in 5G because we need very high reliability. So there will be a lot of base stations deployed very close to each other, okay? So that's called network densification or ultra-dense small cell networks. Multi-connectivity that I just talked about, and those are some of the hot topics in the area. Virtualization, network function virtualization. I think this one, many of you know? Yes? Yes? Okay. So network function virtualization is, again, you try to virtualize. You try to form those functions in software. And millimeter wave, that is, you see, there is a lot of data being generated, and then the spectrum that we have, spectrum is the frequency band that we transmit the data in the wireless network. So the spectrum band is becoming more and more crowded, okay? So 5G will make excessive use of millimeter wave, which is from 30 gigahertz to 300 gigahertz, so that you have more spectrum for transmission. There are a number of technologies there. Okay, this is actually about network slicing here, where you try to allocate different resources for applications that require very high bandwidth and for applications that require ultra-low latency. And for some applications, energy efficiency is more important, that you consume less energy, right? And then for some applications, it might be ultra-high bandwidth, which is the most important one. Okay, now let's come again to vehicular networks, the computation perspective. And I'll be talking quite a bit about vehicular networks. Vehicular networks are very important and also very interesting because vehicular networks, they as well, of course, put some kind of demand on the resources to be provided by 5G networks. They will also say, okay, we need to transmit so and so much data, so we need packet loss rate of 10 power minus 6 and such. But at the same time, it's a very special type of network because the vehicular networks or vehicles, they also have resources to offer for 5G. So 5G and vehicular networks, they go hand in hand. Okay? That was the computation thing. And from communication perspective, there is this very hot topic right now called connected vehicles, and more recently called Internet of Vehicles. So what is connected vehicles? Connectivity between vehicles. We talked about Internet of Things, where things are connected, right? And the vehicles are connected here, which means the vehicles can communicate, the cars here, the buses here, the trucks here, they can communicate with each other, and they can also communicate with the infrastructure, the base stations or the roadside units, okay? Again, we'd like to see a little bit more about why there will be so much data, 1 gigabyte data per second, or so and so many terabytes of data per second. That's, it doesn't come out from nowhere. There are so many sensors. A vehicle is nothing but a swarm of sensors. At least a modern vehicle is, okay? And there are all kinds of sensors here, battery sensors, airbag, driver monitoring sensors, and what is this? Acceleration, deceleration sensors, all kinds of sensors. So they do continuously generate data, and it'll be a lot of data. And so then these vehicles are connected to each other. They are also connected to the infrastructure, base station, or the roadside unit. And they are also connected to the internet, the core network, okay? And this whole thing where they are connected basically to vehicles and infrastructure and the core network, that's called Internet of Vehicles, which is the convergence of mobile internet and the Internet of Things. Okay. So so Internet of Things is also, Internet of Vehicles is also quite a big area. There are some very interesting research challenges and research questions in this area as well. But because this is a very big area in itself, there are many underlying paradigms or many technologies that must work as well for this for the Internet of Vehicles concept to be realized in practice. Software-defined networking. I'm sure some of you at least know about software-defined networking. Yes? No? Okay, software-defined networking is the abstraction. What you do is usually the routers or the switches, they have to transmit the packets from one place to another, but then they decide how do I send this packet further? Do I transmit it to this switch or to this router or to another router? And they have to do a lot of decision making. Thinking and decision-making. But with software-defined networking, what you do is you abstract the decision-making process. So you say there is a control center or a controller that has an overview about what is happening in the network globally, and that will tell you, okay, you just transmit the data, I'll tell you where to forward it, where to transmit it. Okay, so that's software-defined networking, and that is also one of the key functionalities or key technologies behind Internet of Vehicles, also in 5G, actually. Mobile edge computing, I'll be talking a little bit more about it. So I'll explain about it later. Big data was very hot. Well, it is still hot, I guess, but then now people are not talking only about getting big amounts of data, but I think people are trying to make sense of the data that you can get. It doesn't necessarily have to be very big, but whatever data you can get, how to make sense of that, and how to make more sense, how to derive more logic from what you have, from the little data that you have. AI, of course. Cloud computing and many other technologies, including conventional wireless sensor networks, and others. In this lecture, in this talk, of course, we are focusing on AI and mobile edge computing. And mobile edge computing is also an upcoming area where there are quite a few very interesting research problems and challenges. So what exactly is mobile edge computing? Mobile edge computing is basically about pushing computation and storage resources to the edge. Now, what is edge? You have the core network, or you have the cloud, and you have the end users. So the end users are the edge, or near the end users, that's the edge. And then the core networks, that's kind of remote, right? And you want to put not all, but a part of the computation resources, storage resources, or even communication resources closer to the users. That's the concept, basically. And then also, well, we know that edge is closer to the users, but then how close to the users, or where exactly is the edge? That's a discussion in itself. But here, as you can clearly see, the devices, and then the edge network, and then the cloud, which is the central network. And here, the computing power and data storage, the resources basically, they get higher when you are closer to the cloud, and they get less when you get closer to the end users or the devices. So in mobile edge computing, which is also one of the, again, very hot areas, what you usually do is when you get some requests, either for data processing, computation, streaming, any of that, what you do is you try to execute some of the tasks locally here, for example, at the vehicle itself, if the vehicle is sending some request, and then you try to send some of the resources to the cloud, to the core network or to the cloud, and then some of them you try to execute at the edge. Does that make sense? Does that sound logical? Yes? Okay. And how do we categorize those tasks? How do we divide the tasks? Would somebody like to share? What do you think? Okay, there are different ways to there are different ways to divide the work. But if you are the end users, then those tasks or those tasks that need to be executed within a certain deadline, or the latency has to be very small, those you probably prefer to execute here, and those that can withstand some delay-tolerant applications or delay-tolerant tasks, those you probably want to execute here, and then those in between you probably want to execute here. That's one way to look at it. But there can also be a different perspective, because those tasks that need to be completed within 3 milliseconds or 5 milliseconds, probably there are also those tasks that are resource intensive, or they need a lot of computation resources, storage resources, maybe, right? In that case, you cannot afford to execute them in your vehicle. Maybe, I'm saying, maybe or may not be. If it's as simple as the delay-sensitive tasks, they are not that computation intensive, then of course it's simple. You would do it that way. But there can be different criteria, there can be different ways. So here, if you have 10 computation tasks, maybe 2 here, 5 here, and then 3 here, okay? But then in reality, in practice, it's a much more complicated environment. It's not just one vehicle, it's multiple vehicles, and all the vehicles, they are trying to, they are sending the request to the edge network and also to the cloud network, and so what the execution time and the transmission time of what this vehicle has sent will also depend on what other vehicle, so it's a very complicated environment basically, and resource allocation, scheduling in mobile edge computing, that is also a very hot area. Okay. AI for next generation networks. So what did we talk so far is communication networks, they play a crucial role in enabling, in bringing about the revolution that is possible with AI, because you need to, yes, send the data somewhere else. You cannot generate the data and keep it with yourself. And we did see what role communication networks play, or next generation networks play. But in this case now, we will I'll give you an example about how AI can help next generation communication networks, okay? It can be used for a number of different reasons, different applications. Channel state prediction is one of them. In communication networks I'm talking about. Channel state prediction is you have the wireless channel and you don't, so what will be the state of that channel in next iteration or next time slot? That's, you try to predict it more accurately, and the more precise you can predict it, the better you can utilize the channels. So that is one of the applications. Network traffic classification. When I say network traffic, this is packets, communication network classification, that is, and also prediction, equally used for prediction. And for vehicular networks, again, there will be packets as well that you're transmitting for the data packets and also the signaling packets, but also the traffic flow, and here the traffic is the vehicles. And you can also use AI for traffic flow prediction, speed prediction as well. Demand prediction, demand of resources in communication networks as well as other next generation networks, and resource optimization and management, okay? And this one applies also for mobile edge computing or other networks, and many others. Okay, I would now like to talk about one of our recent papers here, where we use AI for a transmission scheduling in a cognitive IOV network, cognitive Internet of Vehicles network. By now we know that IoT platform plays a crucial role in realizing many upcoming or emerging applications and systems. Intelligent transportation systems is one of them. Connected vehicles paradigm is one of them. But then, the need of continuous communication, monitoring, continuous data transmission, that makes it quite challenging, also in terms of the spectrum resources. Okay, so we need the spectrum to transmit the data. Yes, right? And there is something called cognitive radio. Cognitive radio technology is a potential approach to, not to solve it completely, but at least it can alleviate the strain on the spectrum resources a bit by making better use of it, by making better use of the underutilized spectrum. So I'll explain very briefly about cognitive radio networks. Have you heard about cognitive radio networks? Some of you? Okay, many of you haven't. Here is a system called the primary system, and it has a base station. Well, it will have many base stations, but I'm showing one, primary base station. And this is called the primary base station, which in some sense gives you an impression that it has a priority over something else, right? Because it has its own spectrum. Spectrum is the resource, and it owns the spectrum. It has both the spectrum, or it owns the spectrum. But the spectrum in this domain, or in this system, is rather underutilized. It's not used all the time. One of the examples is actually a TV spectrum, which is very less utilized. And this is called primary spectrum. These are vacant spots here. They are called spectrum holes. Now you have another system here called the secondary system, a secondary base station, and then the secondary users. What happens with these is that they either don't have their own spectrum. They probably just use the unlicensed spectrum, 2.4 gigahertz, okay? Or they have some dedicated spectrum, but maybe they have so much more traffic that they would like to make use of, other resources or other spectrum if possible, if they can get it from somewhere. And this is called a cognitive radio network. The secondary, well, actually the whole network is called cognitive radio network, but the secondary system is responsible for being cognitive, so that it can detect those spectrum holes over here, which means it can detect when the primary user is using the spectrum and when the primary user is not using the spectrum, and it can use the spectrum when it is vacant. Okay, so this is a little bit simplified version again of what a cognitive radio network is, but I think that's sufficient enough for the paper that I'll be talking about. Okay. All right. So in a vehicular network or in an IOV, efficient data transmission scheduling, it faces a number of challenges. The first one, and the most important one, is highly dynamic topology due to vehicle mobility, right? Even when we move, we carry our mobile phones, and when we walk, the mobility, that brings in a lot of dynamics because of the motion. But then when the vehicles are moving, they're actually moving very, very fast. So the channel conditions change, right? And even if you have demanded some resources, when the resources are allocated, probably you are already out of that zone of that RSU. It becomes very dynamic, highly dynamic. And in this case, what we are trying to do is, in addition to using your own spectrum, you are also trying to be cognitive. Okay, the IOV, the Internet of Vehicles network, is trying to be cognitive so that it can detect. If there is a primary system, then it'll try to detect when the primary user or the primary system is not using its spectrum. And then it'll try to use the spectrum when it's empty or when it's vacant, okay? And there are certain conditions that if the primary user returns, then you have to give it back, you have to immediately release the spectrum, and it has to respect all those conditions. And uncertainty in available resources and its demand. Again, it's not just one vehicle moving on the road, it's many vehicles. So there is this uncertainty about the available resources as well. And I mentioned V2X communication here, but that's mainly related to the modes of communication. Vehicles, they can communicate with other vehicles. It's called V2V mode. And vehicles can also communicate with the infrastructure, the base station or the RSUs. RSUs are the roadside units. Okay? So there are many different variables here. Okay? Did you get that? And then, of course, the strict QoS requirements, performance requirements, packet loss rate and end-to-end latency. So there are a lot of challenges there, basically. Now, in this paper, it's a very recent paper in IoT journal. We propose a deep Q-learning approach for designing a learning-based optimal data transmission scheduling in cognitive radio vehicular networks to minimize the transmission costs while also making use. Yes? One second.
In the last slide, you mentioned that some of if the spectrum is free, then another base station could use it, right?
Yes.
So how do you know that the spectrum is free or that the owner of the spectrum is using it?
Okay. Well, that's a very good question, and I'm glad at least one question came up. Yes, there are different techniques to do it actually. The simplest one, cognitive radio was again a very hot topic in 2008, 9, 10. Now it's kind of saturating, but still people are using it in the context of different newer topics, along with newer topics. But there are different ways to, coming back to your question, there are different ways to detect how the spectrum is vacant. One of them, the simplest one, is called energy detector. So what you do is you listen to the spectrum, to TV transmission. TV spectrum is one such spectrum which is occupied very less or used very less. There can also be others, but with other spectrum it's a little bit more difficult because it's occupied more often, and also it's a little bit more dynamic than TV spectrum. But you can listen to the TV spectrum, which means you basically get the signal when the broadcaster broadcasts the signal, and then you calculate the energy level, the energy of the RSSP receives signal strength. And then you compare that with a certain threshold. Okay, you set a threshold that depends on, again, a lot of factors, the noise level of the device and many different factors. But then you compare that with a certain threshold, and if it exceeds that threshold, then you say that, okay, I think there is the TV signal present, and if it's less than that threshold, then you will say that it's actually empty or vacant. But it's not the decision, what you think is correct may not be 100% correct. There is something called probability of false alarm, and there's something called probability of misdetection. So you might as well issue a false alarm when the TV signal was actually not present. Okay? So it was not present, but because of the threshold, something happened, there was probably some noise, and you decided that the signal was present. And then you will not use the spectrum, which means you wasted it. Right? And that's called false alarm. And there will be a certain probability of false alarm. And misdetection is the signal was actually present, but then, again, because of the threshold, because of the noise level went down or something, you will think that the signal was actually not present. But then there are conditions on what are the protocols. There are certain protocols. You thought that there was no primary signal, but then you started transmitting. And then it will interfere the primary signal. But then you will have to leave. You will have to release the channel because it's actually not yours. Okay? And then that is just one of the detection methods. There is something called feature detector and others as well. But yes, that's a different topic. Okay? Did I answer your question fully? Yes? Okay. Yes? There?
From your previous slide, it says there that there is a requirement when it comes to the quality of service. So from the user's perspective, if we buy services like for telco. So the telco will sell us reliability is 90 or towards 99.99%. So in our case, if we're using the service and in some period of time that we have latency in using, for example, data. So it's just a matter of the business telling us that they can provide us that reliability. However, for the user's perspective, we are not totally using that reliability. It's just a matter of the quality of service pertaining to the terms of services being offered by the telecommunications provider. So it's just a marketing or sales in that perspective from the user's perspective. However, from the producers or the one who is providing that services, it's just they prove that it can have reliability for 99.99 or something else for the 5 nines or 6 nines. So it's just how it is that most of the users are not experiencing that reliability.
I'm sorry, I didn't quite get your question.
The reliability of the service. Reliability of the service. When you say quality of services, right? QoS. So most of the users are not experiencing that 99.99999% reliability.
So what is your question?
The question is, it is proven that the service will be that the service is reliable. However, when the user is using the service, we are not experiencing that 99.99%.
Okay. Okay, well, I'm still not sure if I understood your question 100%, but I'll try to
I think if
to
I
answer.
may, what he meant is when you showed 99 point certain number of 9% as the reliability or the quality, so that's what he says, I think, is it's measured some way, but what he's suggesting is perhaps that's not the reliability the users are getting. And if it's so, why is there this discrepancy?
Okay. Yes, all right. Yes, that's true. In general, that can be true. The thing is, there are two terms. One is quality of service. The other one is quality of experience. Okay? And the two are very closely related, yes. But then quality of service is the term that is from the network's perspective or the telco's perspective. And then there are certain measures, measurements carried out from the network operator or from the telco company, and that is from at the network infrastructure. But then again, from the user's perspective also, it may or may not be possible to measure the quality that each and every individual user is experiencing. But the quality of service metrics, and then even within QoS metrics, there are multiple metrics actually. Packet outage probability and end-to-end latency, they are just two of those. Jitter is another one. There are a couple of them. But then the QoS is, in some sense, I'm not sure if it would be precise to call it average, but in some sense it is a kind of average, or it is kind of the overall QoS. But then for users it might be slightly different, yes, but also one user might be experiencing it differently, and then the other user might have it very good. It also depends on where you are, where this user is, and where that user is. For me, if I'm in a metro that is 3 stories underground, and then if somebody is downtown, then the QoS may be different. Of course, the network operator or the telco will have some numbers that'll say, okay, if you're underground, it may slightly decrease or will decrease by 1/9 and so forth. But yes, those numbers, those can be slightly different, QoS and what the user perceives or experiences. And there has been quite a bit of discussion about QoE, or quality of experience, should be the actual metric and not QoS, but then it's from the network operator's perspective versus the user's perspective, yes. And that's okay. What you said is actually true. But these are two different concepts. And then from the network operators, they basically try to focus on QoS, but I think the concept is changing a bit. Also in terms of marketing, and also in terms of, because eventually the services are for the users, right? If the users don't buy it, then, so yes. Okay, shall I go ahead? All right, I think I finished this one. Oh, okay, only have 15 minutes. So this is a scenario that we are considering. We have a number of vehicles running along this road, and the vehicle is divided into a number of segments here. Each covered by an RSU, roadside unit. There are MRSUs. And each of these RSUs, they have a cognitive radio device in it, and that means the RSUs can sense the signal from either TV spectrum or the primary users, and they can use it when the primary users are not there, or when they decide, when they think that the primary users are not there. And the RSUs, they are connected to the servers here. And each of the vehicles, they have a queue with them, and the queues there are multiple queues for different kinds of data. And here, when we say different kinds of data, we focus on the latency. So we say, okay, there are some very highly delay sensitive data, and some moderately sensitive, some less sensitive, and then those will be stored in different queues. Okay, multiple queue system, and each data is characterized by BJ and TJ, where BJ is the size of the data, and TJ is the latency or the time constraint. Then the data rate for transmission from vehicle V to RSU M on a licensed V2I channel. So even in vehicular networks, there is a licensed channel, actually. It's called DSRC, Dedicated Short Range Communication channel, that it's at 5.9 gigahertz, and it has a bandwidth of about, I think, 75 megahertz in the US, and in Europe, 30 megahertz. So it has a licensed spectrum, but then because there will be so much more data, so then we try to also make use of the cognitive radio channel or the primary user channel. So we are using cognitive radio technology here. So then we have two different data rates. One is V2I, vehicle to infrastructure communication, but using licensed band. Okay, so this is the data rate, and this is Shannon's formula. Yes? Okay, so this is bandwidth and log 2. This is the transmission power in V2I mode, and this is the path loss per unit distance. This is distance between vehicle V and RSU M. This is the noise power. If you use the CR channel instead, the primary user channel, and not the licensed channel, then it will be, you will have to integrate it over 0 to tau. Tau is the length of the slot or length of the frame. And that will be a function of the probability that the time that the primary users do not return to their own channel is greater than a certain threshold. Okay? And data rate for V2V transmission from vehicle V to V dash. So this is a transmission from V to V dash, but they don't use cognitive radio channel because it's only the RSU that has the cognitive radio device. Vehicles don't have it. Okay? So for data rate for V2V channels will be here. This is the transmission power and path loss per unit distance, and then this is the noise power. Okay. This is noise power here. Here you must have noticed that it's usually the SINR, signal to interference noise ratio. But in this case, we are assuming that there's no interference between different segments. Okay, and also we are assuming OFDM, orthogonal frequency division multiplexing. So then there is just noise and no interference. But in case of V2V transmission, this part over here, that is the set of other vehicles that communicate in the same channel within the interference range. So when you transmit, you might as well have some interference. Our objective in this paper is, there are two main objectives. The first one is, of course, QoS, or maybe it should have been QoE, but in the paper we have QoS, which is the delay constraint that should be satisfied. And the second one is you want to make efficient efficient use of the spectrum. Now here, we use deep Q learning. So Q learning is a kind of reinforcement learning, but it's you must have learned about different reinforcement learning algorithms as well, techniques as well, in the previous lectures. But what you do is, in reinforcement learning, you try to learn as you go. So you take an action and then you get a reward, or sometimes you get a punishment. So then you will eventually figure out, oh, if I do this, this is right. If I do this, this is wrong. So we do introduce a reward function as well. Actually, it's a negative reward function. It's a punishment function. So what we do is, if you are not able, as a vehicle, if you are not able to transmit the data that you have in your cache within the specified deadline, and that may be different for some data which is really sensitive, you may need to transmit it within one time frame. Our time constraint is in terms of time frames and not in milliseconds, so it's not absolute metric, it's a relative metric. But then if you don't transmit it within one slot, which is probably 10 milliseconds or 20 milliseconds, then you get so and so much punishment. But for delay tolerant data, then you can probably take 50 milliseconds or 5 slots or so. So this is the punishment function here, where okay. So there are two main variables here, x and y. X means, both of them are binary variables, which means it's 1 if vehicle V on road segment E at time frame L transmits data using a cognitive radio channel, primary user channel, okay, in V2I mode. And YLV is the same thing if vehicle V transmits a packet or data from road segment E at time frame L, using a license channel in V2I mode. So CR channel and license channel, but both of them in V2I mode. So here you see, this is actually the data rate, normalized data rate actually, the amount of data that you can transmit in V2I mode using the license spectrum, which is this one, Y. And QV is the amount of data that you should have transmitted. And this is how much you were supposed to transmit, but this is how much you could. Okay, so then you get whatever was not transmitted, and then you multiply it with binary variable y. Okay, and the same thing with this one. This is the data that you couldn't transmit using either of the modes. So this is a punishment function basically, or negative reward. And then we try to calculate the loss here, where W and CV and CC, they are the unit prices. Whatever data you couldn't transmit, HL. Okay, let me put it like this. Whatever data you couldn't transmit, that was HL from the previous slide, you will pay W units, W cents per unit of data that you couldn't transmit, which was calculated from the equation before. And then this one is the data that you transmit using the license channel, and this is the data that you transmit using the CR channel. And then these are the unit prices, CV and CC here. If you use the license channel, then it's CV. If you use the cognitive the primary user channel, then it's CC. CV is greater than CC, naturally, because the opportunistic channel should be cheaper, right? So this is the total cost that you pay. And loss is probably not, again, the appropriate term. I think it should have been the cost. In the paper, we kept it as the loss, so I'm still keeping it the same. Okay? And these are the constraints, which says that you can either transmit using only one of the modes. Only in V2I mode using license channel, or V2I mode using the cognitive radio channel, or V2V mode. Okay. So here, yes?
I have a question. Regarding, can you please go back to your previous slide? Yeah. So you use reinforcement learning, right? So I believe it takes a lot of iterations to train the model. So how is it feasible to train such a model in this scenario, for example?
Yes, that's exactly the motivation here. So what we do is, it is kind of reinforcement learning, but then we use the Q function. So what we try to do is, we have the states, possible states and possible actions, and we try to do a bit of matching between the states and the actions. But eventually, even with Q functions, if there is a lot, if the state space grows, if the number of actions and the number of state variables, they grow, then eventually even using calculating the Q table, that'll become quite computation intensive, which is true. So then I think I can probably, maybe I have that coming in my following slides.
My question was like, do you train, how do you train it? In the simulated environment, or, in the real world? It's something like you are transmitting the data, right? It's something that goes into the real world, right?
Yes.
So do you train your model in the lab or in the simulation, or you do it How do you do it?
Okay, for this paper, we simulated it. We didn't do it. We didn't train it using the data. What we do is we have the different states for the channel, for the primary user channel, and we also have a set of possible actions and possible states. And then we try to do the strategy mapping, the states and the actions, and then we try to, of course, take the action that gives you the best value or best reward for every possible from among the possible actions for given each state, right? But then when the number of states, because there are so many variables in this case, even if it's simulation, we are not using real data, but when you simulate, then there is some data coming from every iteration or every possible state and every possible scenario. So you try to record that as you run your simulations, and then you run it, okay. With Q function, you basically try to, yes, you basically try to do the mapping, but then because the strategy space is so big, so what you basically do is we try to approximate the Q function, and for that we use the neural network. So there is some overhead there, for sure, yes, but then but we still believe that this has less overhead than training it using the,
Thank you.
the actual data, yes. So this is where I was coming to. Okay, we use the MDP here, and this is the state of the MDP at frame L, where this is the caching state of vehicle V at time frame L, and this is the set of vehicle positions in time frame L. This is the action taken by the vehicles, and the action here is the communication mode that you choose, V2V or V2I, CR cognitive radio channel or the licensed channel. Yes, and then you try to find your optimal transmission policy. Okay, the discount factor. And this is what Vinod sir was asking, I think. We adopt the Q-learning process, which is an offline reinforcement learning technique. But then it becomes cumbersome if your state space is large, because the total number of combinations is the product of the dimensions of each variable set. And then we use deep Q-learning, where what you do is see two different things, right? Q-learning itself is an offline reinforcement learning, where you try to say, okay, if this is my state, then I have three actions to choose from, then in this state I'll choose this one, but if this is my state, then I'll choose these one from the three possible actions, and so on. That's offline. But then with deep Q-learning, what we do is you cannot calculate the Q function, the exact Q function, but you try to calculate an approximate value for the Q function, and for that you have to, okay, it's here. For that you have to use the neural network. All right, and there are more details in the paper, of course, if you would like to read, but I'll go to the results here. So these are the parameters that we used for our simulations. 3 RSUs, 3 segments basically, and 5 different types of data generated, which means they have their time sensitivities are in 5 different scales. Okay, so within 10 milliseconds, within 20, within 30, 40, and 50. Then vehicle speed, 100 kilometers per hour, and then other parameters here. And some results that we have here, and the take-home message is the average transmission loss, that is less when we use deep Q-learning approach. That's this one. And also the conversions. So it does take some time, actually. So what Vinod sir pointed out was true. It does take some time, but it was about 15,000, depending on the value of row, from 15,000 to about 20,000, 25,000, and that was about 25 minutes in a machine with these specifications. Okay, I think that was what I had to say. Questions?
So I was just wondering about the underlying protocols for what they use for the Internet of Things, because I know, like, for the legacy Internet or the normal Internet, we have the TCP/IP, but a lot of people are trying to replace that because that's supposed to be something that was invented in the 70s, and I think the next generation networks are a very good place to have a new protocol. So is it still running on that protocol, or do we have new protocols?
Yes, that's, I think, a never-ending debate, kind of, because there are people who probably they are from 70s or earlier, so they always like TCP, TCP/IP protocols. So some people believe that we should borrow something from what exists, and there are people who are designing better protocols for the wireless environment, and even in University of Oslo, we have colleagues who actually think that TCP is completely useless, at least as of now, and they are working from scratch, trying to develop new protocols that can provide reliabilities as good as TCP, but at the same time, probably not as much overhead as TCP. So, and then there are people who say, okay, why do all the work from scratch? You probably should, do some kind of borrow. So this is a kind of never-ending debate. I think it's still, certain things are standardized, certain things are still, yes. Yes, the existing, because if you just say IoT, then what exactly is IoT? That has to be specific, right? For vehicular networks, for example, then it's an Internet of Vehicles, but then there are protocols for vehicular communication, VANETs, and right. And if it's a communication network or 4G or LTE, I'm talking about the wireless network, of course, then we are using the protocols from there onwards. And when we make the transition from 4G to 5G, then certain things will change. We will be making use of newer technologies such as millimeter wave, network function virtualization and slicing and such. But then we're not probably changing everything that exists. At least that is what I believe. Yes. More questions?
Excuse me, with autonomous vehicles, right? You said that it was generating 1 gigabyte of data. Is it uploading like 1 gigabyte of data per second, or is it generating that data?
Yes. Autonomous vehicles, although there has been a lot of work in the last decade, especially last 5 years, but as we all know, there has been many pilots, many experiments, but autonomous vehicles are not running on the roads as of now. There has been some experiments, I know, but then it's not yet commercially deployed yet. That is the 1 gigabyte data thing, that is the amount of data that is generated, and some of it may be consumed or used locally, of course, but a lot of it has to be uploaded to the cloud. Not to public cloud, but if it's a Volvo vehicle, then it has to go to the Volvo cloud, or if it's another manufacturer, then it has to go to another manufacturer's cloud. So that is exactly the challenge. I mean, if all the vehicles will be autonomous vehicles, then every vehicle is generating 1 gigabyte every second. So you don't have to probably upload 1 gigabyte. Maybe you can use half of it, or maybe you just, let's say the best possible case, so you just send 200 megabytes, or even slightly less. Let's say 100 megabytes. Let's be the best of the best, the most optimistic. But even then, if it's 100 megabytes and all the vehicles need to transmit, there will be some kind of congestion, for sure, right? And that will only get worse. And these are the things that are quite challenging, despite the developments in different aspects of technology and hardware, and yes. But that was the data that is generated.
Okay. Another question is, when a car or a vehicle like generates that data, right, and it needs to be uploaded, right? So is it all going to be like very high priority data that needs to be uploaded at that time, or is it going to be like we can segment the data? Can we not segment the data into something that needs to be uploaded like in real time, and maybe some other data that can be prioritized later?
Yes, absolutely. That's a very good question and a very good remark, actually, because all the data, first of all, yes, you can use some of the data locally, but even the data that you need to upload or that you need to send to the controller or the server, not all of them have the same QoS requirements, okay? So for some of them, the latency requirement might be very critical, especially, for example, in the case of accident avoidance or some safety critical messages. Then the delay might be very critical. Both delay and the packet reliability will be very critical. But then those are not the only data generated or used or consumed in vehicular networks. There will be data about infotainment, about map updates, about others, information, and that is not as critical as the safety-related information or accident avoidance information. So those can be probably transmitted a bit later, or even if you lose a few packets, the correlation will be very high. at least fairly high, so you don't lose that much information. In that case, the packet loss rate does not have to be 10 power minus 9 or even minus 6. It can be probably 10 power minus 3. So yes, it's different, but still, so what we are saying is if all the vehicles, when they self-drive, everybody has to upload or needs to upload, does upload 1 gigabyte per second, then it will be simply impossible. But then there will be certain segments, there will be certain things, but even those that for which the packet error probability and latency are not the most important ones, but they probably need higher data rate, for example. Okay? The ones that you need to send within 10 milliseconds or 2 milliseconds, they probably are short packets. We call MTC, machine type communication. Very short packets, so you don't really need that high data rate. You just transmit a few bytes, but then they have to reach, they cannot be lost, and they have to reach within milliseconds. That's a requirement. But you don't need a big bandwidth. But then there might be, the maps and other infotainments. So it doesn't have to be within few milliseconds. Well, it has to be within milliseconds, but not within 10 milliseconds or 5 milliseconds, but they probably need a higher bandwidth. So you can do them later when the data rate is available, but if everybody is doing it, then you just think about it. Congestion is more likely to happen than not.
If you need like 100%, accuracy, like you cannot have any packet loss, right? And it has to be guaranteed that, some data has to reach the destination, right? So is there a solution to using, alternative to using like something like a TCP protocol, where is you send the next packet after you...
The previous packet is received, it's acknowledged?
After the acknowledgement, yes.
Well, yes, why not? That is certainly one alternative, I would say, but it's not as straightforward to use a TCP-like structure here. The biggest problem with TCP is the acknowledgements. You see, with UDP, it's not the biggest problem, it's the reliability. That's actually an advantage, but the same thing is also a problem, because with UDP, you send it, you use the best effort, but then you don't know whether it's received or not received, right? So there can be jitters. But then with the TCP, you try to acknowledge that the previous packet has been received, and that adds a lot of overhead. That's why TCP is becoming less and less liked by people. And yes, it should be possible. Are you talking about vehicular networks in particular, or general communication networks, or general next generation networks?
I'm talking about like especially vehicle networks, because the data has to go through a wireless channel, and with like a smart home or a factory, then it can go through a fiber optics. Then
that's okay. Yes and no, both. Yes, because if you can do that, then the reliability thing is kind of a guaranteed. But it's not theoretically, but it's not possible in practice, because, see, what will I do? I'm transmitting a packet, then I'm waiting for the acknowledgement. I don't get it, then I ask again or transmit it again, and then I'll only stop when I get the acknowledgement, right? But with vehicular networks, they are moving. Yes, so they are moving. This mobility is the biggest factor. Even when you are stationary, actually, when I am a person carrying a mobile phone, it's very hard to get 100% reliability, or even 99.49 or 59s. We saw those numbers where we needed 6 different paths, each with 90% reliability. So I should connect to 6 different base stations, and that's a lot of redundancy. It's very costly. Ideally, if you have all the resources, theoretically speaking, hypothetically speaking, if you have all the resources with yourself, you do all the processing, you have the control center, then you can get it within microseconds, right? But then that's not cost effective, that's not practical. So that is why the idea of cloud came up, and then it became so popular, right? But then if you wait for the acknowledgements, then with vehicular networks, especially with delay sensitive applications, your deadline will be already expired, before you get the acknowledgement. So the timing is very critical here. So it should be hypothetically possible, but then practically, because you need to get it done within such a small amount of time, so it's not that practical.
And you also talked about like 3 millisecond latency from the vehicle to like the computer center, right? Sorry. Okay.
I think you can discuss later offline, because so that we give other participants opportunities if they have questions.
Yes, more questions?
I abuse my power to ask one question.
Yes.
Thank you for the talk, first of all. And so when you showed some of the slides regarding Internet of Vehicles, it seems that we're envisioning a system in the future where most of these autonomous vehicles are interconnected, and even the traffic flow might be dependent on the communications. Is that so or not first?
Do you mean the vehicle traffic?
Yeah. I mean, because the accidents and all these systems are being monitored or being controlled.
Yes, absolutely.
So if we look now for ourselves also, we use lots of Google Maps and stuff, and what that has made is we start becoming dependent on it. So people who are so used to using GPS maps, they struggle to find their way when the system is not working. So how is the research, the people working on fault tolerance in these systems? Because if we, in many years, if we have these big systems controlling all the network flow, and then if it fails, what's the fallback systems? That they work normally, or are we going into a complete chaos? Is it too early to think about these systems?
And I think it's too early to think about, and again, I'm very glad this question came up. A fault tolerance or robustness of a system, even in a general sense, probably not necessarily limited to the case of autonomous vehicles or autonomous driving. For general networks where reliability of communication and reliability of driving, the reliability part or the robustness part is so important, fault tolerance part is so important. Yes, if you are relying on only one alternative, and if that alternative or that path, it doesn't have to be multiple communication paths, it can be other different paths, some kind of redundancy there is necessary, I would say. Unless you have algorithms, you have techniques where you can make predictions and where you can provide some kind of bounds on the predictability of the performance, reliability performance, or predictability of the robustness performance. So what is actually important, which I didn't include a lot of things because I wanted to cover a couple of different things in the talk. But what is important when we only say reliability or robustness or resilience, that's actually an incomplete notion. It's not about reliability or robustness, it's about predictability of the reliability performance, or predictability, or the accuracy of predictability of the reliability performance. So if you can provide me a bound that my system or your system, even though it has only one path, can get you a fault tolerance level of 99.99999%. Before we were talking about packet outage rate and packet reliability, but then fault tolerance, it's not exactly the same, but we can relate, I guess. So if you say that this is possible, if you guarantee it, even without any redundancy, which is rather hypothetical, I would say, but if you guarantee that, then I would assume or I would expect that the system will not go into complete chaos. Because 0.000001% or 10 power minus 6, 10 power minus 8, that is kind of, you probably take chance with many systems. But then that would be hypothetical. I say there has to be some kind of redundancy, some kind of fallback, some kind of, or even if the chaos happens, there has to be some kind of a mechanism to limit the impact of what happens. And that applies to many different systems, many different networks, including, well, autonomous driving, also including smart grid. So this limiting the impact of what happens is very... For autonomous driving?
Yeah. Or is it too early to work? Because I think...
Okay.
It's kind of fallback systems and notions of what could be some examples of fallback systems when everything is connected and being coordinated with the central system.
Yeah, okay. I personally, there has, we actually, I have hired, we've hired 3 PhD students recently, and we are actually working, recently we started working on advanced vehicle safety, which is again for connected vehicles. And so it's not just, we have the safety systems in the vehicles, stability controllers and safety systems, but then those are not sufficient, those are not good enough. And we are working on making that system even more advanced, but that's kind of advanced vehicle safety. In a connected vehicle paradigm, and especially for the case of self-driving, I'm not quite sure if there has been, at least I'm not sure if there has been works that are published already. Maybe people are still working, maybe not. And I think people would consider that a system of chaos, will have to consider that at least eventually, but maybe as of now, I'm not sure if I have seen any work on that. Yes, more questions?
Thank you.